Oh, and I should share my screen. So, let's see if this works. Okay, great. I don't know why it's like 10% of the time it refuses to work over the cable. And so now I'm just like, okay, is it gonna work? Is it gonna work? I don't know. But this time it worked. All right, great. So I hope everybody had a good break. Somehow they're never as long as you think they're going to be, but you know, it's better than not having a break. So let me just remind you, last time what we talked about was Lie groups and their actions on manifolds. And that was sort of with a view toward how these show up in symplectic geometry. Sort of symmetry is a very important idea in symplectic geometry. And I believe did we mention, I forget now whether I mentioned this before, but I'm definitely mentioning it now, that, well, one of the kind of natural questions is when I have a group acting on a manifold and that manifold has a symplectic form, what's the natural kind of compatibility to look for between the action and the symplectic form? And of course, there's one obvious such compatibility. You can require every group element to act by a symplectomorphism, right? If you have a smooth group action on a manifold, every element of the group acts by a diffeomorphism. You can pull back the symplectic form by that, and well, either it stays the same or it doesn't. So we've already covered some examples earlier in this course. I mean, we talked a lot about symplectic actions of R, sort of is how Hamiltonian mechanics works. So one ready supply of these is if you have any group action on a manifold, you get a symplectic group action induced on the cotangent bundle. And these are pretty important in physics, right? You can think of group actions in physics as some kind of symmetry of your underlying space, and then the induced symmetries on the phase space will automatically be symplectic. So ones that come up a lot is R3, you know, thought of as the world, has an action by translation of your coordinates or by rotation. So the translation action, that's by the Lie group R3 with addition. And then the rotation is what's called SO3. So it's the orthogonal 3x3 matrices with determinant 1. Every one of those corresponds to a rotation in R3 around some axis. Another example which sort of feels similar, but is actually quite different. So SO3 is acting on all of R3. It preserves spheres of a given distance from the origin. And well, those spheres are surfaces. They have a unique SO3 invariant volume form up to scaling. That gives you a symplectic form. And the action of SO3 is symplectic because the volume form is invariant under it. And another one that is worth mentioning is if I take a circle times a circle, that again gives me a surface. So a symplectic form on it is just induced by a volume form. There's sort of an obvious volume form on S1, an obvious volume form on S2. When you take the product, you get a symplectic form on the torus, and that's invariant under left translation. So the torus itself is a Lie group, thinking of it as, the easiest way to say this is that there's two torus, it's the same as R2 mod the subgroup Z2. So that acts on itself by left translation, basically by addition of elements in R2 mod Z2. And that's going to preserve the symplectic form because it preserves the area. All right, cool. So this is just kind of a few examples of symplectic actions that it's useful to keep in mind. All right. So as we talked last time, one of the kind of very useful ways to think about Lie group actions is that you can think about them in terms of their Lie algebra. So just as it was useful to think about flows by thinking about the vector fields that gave us those flows, you can think about a Lie group action by saying, I have this Lie algebra. Every element of the Lie algebra maps to a vector field. And this actually contains all the information about how the connected component of the identity in the Lie group acts. So somehow Lie algebras can't know anything about the Lie group outside the connected component of the identity, but they know almost everything that's going on in the connected component of the identity. So, sometimes you'll slip in this hypothesis that the Lie group is connected because then the Lie algebra controls almost everything that's going on. So in particular, you can get all the elements of the Lie group by taking elements of the Lie algebra, exponentiating them to flows on your manifold, and then multiplying those. So you won't get literally every element of the group by exponentiating, but you'll get generators of the group. All right, so if the action is symplectic, of course, the corresponding vector fields are going to preserve the symplectic form. They will be symplectic in the sense we talked about before. So let me just remind you, that means that the Lie derivative with respect to this vector field of the symplectic form is 0. And of course it is, because the definition of the Lie derivative is generate the flow with your vector field and see how it changes your form. And when I exponentiate, I get elements of the group, and those act by symplectomorphisms. All right. Now, one of the things we kind of emphasized before is, well, there are symplectic vector fields, but there's a special kind of symplectic vector field, which are the ones that are Hamiltonian, that come from a function on your original manifold. And it's worth noting, if your Lie algebra is non-abelian, then some of your vector fields are going to be forced to be Hamiltonian, right? We saw before that the commutator of two symplectic vector fields is always a Hamiltonian vector field. I hesitate to write this because I would probably screw up the sign, but the Hamiltonian vector field for the symplectic form applied to ZW is equal to the commutator of WZ for Y and Z symplectic. So actually, if, for example, your Lie algebra is simple and G is equal to the span of the commutators, then every element in vector fields. But there might be some elements of your Lie algebra that can't be written as commutators, and you genuinely have to worry about whether those will go to symplectic vector fields that are Hamiltonian or ones that are not Hamiltonian. So we have an induced map. It's actually a map of Lie algebras, with the right-hand side having, since both of these have trivial Lie bracket structure, of G modulo the span of commutators in G, mapping to the symplectic vector fields mod the Hamiltonian vector fields, which we can identify as H1 Dirac. So I can take an element of the Lie algebra, I can send it to the corresponding vector field on the manifold, I can contract that with the symplectic form, and I get a one form, and I'm a Hamiltonian vector field if that one form is exact. I'm a symplectic vector field if that one form is closed. Yes, I did say that correctly. So somehow your room to have not symplectic actions where not everything is a Hamiltonian vector field, kind of the obstruction is both the failure of your Lie algebra to be what's called perfect. So we call G perfect if G is equal to the commutator with itself. So for example, That was bad. The Lie algebra of SLN of traceless matrices is perfect. In fact, any simple Lie algebra is perfect, as long as it's not abelian. Whereas if I take GLN, that's not perfect, because the commutator of any two matrices has trace 0. So the existence of matrices with trace not 0 gives you a non-trivial quotient there. All right. Oh, yeah, I had a reminder about that just a little further down. So this is just to say, like, you know, this isn't an unreasonable thing to ask that every vector field coming from your Lie algebra is Hamiltonian. It will either happen if G is perfect, which happens for all the simple Lie algebras, so SUN, SON, SP2N, all have this property, aside from a few exceptions when n is very small. So I left this out, but that's actually kind of bad. Here I need to have n greater than or equal to 3. And here I need to have n. No, I guess it's okay. These are both just greater than 1. So SU1 is trivial, so not very interesting. All right. Cool. Or I didn't finish my thought there. Or if H1 of the manifold is trivial, then you'll also get that every vector field that's symplectic has to be Hamiltonian. This doesn't happen all the time, though. So, for example, if I look at the case of the 2 torus acting on itself by left translation, that actually gives us the example of a symplectic but not Hamiltonian vector field we had before. So there, the Lie algebra of T2 you can identify with R2, because you're taking R2 and modding out by Z2, which doesn't change the tangent space. And you know, AB in T2 gets sent to this vector field, A times ddx plus B times ddy. And we saw before that this is not Hamiltonian as long as A and B are not both 0. In fact, this is an isomorphism to H1 of T2, which is also 2-dimensional. So this can happen, but in most kind of interesting cases, I guess it depends what you think is interesting, but in many interesting cases, you won't have this problem, and every vector field will go to a Hamiltonian. All right, well, that feels like an important property, right? Hamiltonian vector fields are really important. So should I call a group action Hamiltonian if whenever I take an element of the Lie algebra, I get a Hamiltonian vector field? This is a question. Is that a good name for a Hamiltonian thing? Well, I would say that's not quite right, because a Hamiltonian group action of a 1D Lie group, so that's generated by a single vector field. And, you know, I would say that sort of the right notion there is not just, is your vector field Hamiltonian, but actually choose a Hamiltonian for your vector field. Choose a function so that your vector field is the Hamiltonian of that. That's what this condition says. So for some generator of the Lie algebra, you look at the corresponding vector field and you want to find some H that's the Hamiltonian vector field. Which doesn't seem like a very big deal, right? If you have a Hamiltonian vector field, like the Hamiltonian function is unique up to adding a constant, well, it could be important what constant you choose, but that doesn't seem like a terribly big deal. But for a bigger Lie group, this can be a little bit more of an issue. And this is going to lead us eventually to this notion of moment maps, but I kind of want to take you through like, oh, well, when you're just trying to kind of resolve for yourself, what does it mean that this action should be Hamiltonian, should be naturally led to this notion of moment maps. By the way, are there any questions? I should just pause for a moment and see if. Okay, great. So what's the generalization of this for a higher dimensional group? Well, assume that we have a Lie group G with a faithful symplectic action on a symplectic manifold M omega, and that for every element of the Lie algebra, we get a Hamiltonian vector field on N, which is a, as we saw with the torus, that's an actual condition. So I guess that sort of making this a Hamiltonian action should involve choosing a Hamiltonian function for every element of the Lie algebra. You might say, like, well, that's a lot of choices. So what kind of consistency should we ask for? Well, I think at least a reasonable thing to ask is that the function should depend linearly on the element of the Lie algebra. So if I have x and y in my Lie algebra, the functions corresponding to them sum to the function corresponding to x plus y. So this is the same as saying that taking an element of the Lie algebra and sending it to the value of the function fy at some point m is a linear map from the Lie algebra to the real numbers. So it's an element of G dual, right? So making such a choice is the same as a function from M to G dual, such that I get a Hamiltonian function for y from pairing that function into G dual with y. So in part I'm going through this so you can see, like, oh, having a function into G dual is not a weird thing. It's something you're forced to get if you put on this extremely simple constraint of additivity on our choice of Hamiltonian function for every element of the Lie algebra. Now, there's no obstruction to finding such a thing. It's always possible to construct a map with the property we want to G dual. You could just pick a basis of the Lie algebra G, make a completely random choice for each element of the basis, and then extend linearly. I like to think about this in terms of, you can think about the set of functions on, that's not going to be good. The set of functions on your manifold M such that their Hamiltonian is in the image of this Lie algebra action. So it's the notation here is a little bit funny, but the idea is I have C infinity of M, all functions, and this maps to the Hamiltonian vector fields on M, not injectively with a kernel. I have my Lie algebra G mapping in here. And so what I'm doing is a pullback of this diagram. Right? I'm looking at the pairs of a function and an element of the Lie algebra such that they go to the same place under this map. But this map is injective since I've assumed that that the action is faithful. So this map is also injective. I don't actually have to tell you which element of the Lie algebra it is because the function already determines that. The function gives you the vector field, and there's only one element of the Lie algebra that hits that vector field. So as that diagram showed, I have a surjective map that sends a function to the element of the Lie algebra that hits the same vector field. Right? The element of the Lie algebra such that y sub m is equal to x sub f. That's this horizontal map down at the bottom in this pullback diagram. And this is just a general thing, right? If you have a surjective map of Lie algebras and an injective map into the same Lie algebra from something else, you can always construct this pullback.
Quick question.
Mm-hmm.
We talked about Poisson algebras, right? C infinity of M is a Poisson algebra.
Yeah.
Can you describe? Is a choice of such a thing equivalent to just a map of Poisson algebras? Sorry, a map of Lie algebras from G into the Poisson algebra C infinity of M?
Well, no, because I haven't constructed such a thing. So we're going to get to that.
Okay.
Yeah, what you just said is something we would like to have, but it's not something we're guaranteed to have, precisely because if I have an element of my Lie algebra, I get a Hamiltonian vector field, and that's hit by some function undertaking Hamiltonian vector field, but it's not hit by a unique one. And it's genuinely not true that you can always make those choices consistently to get a Lie algebra homomorphism.
Sure, I mean, because there's up to adding that constant is what messes things up, right? So, okay, I'll shut up.
No, it's fine. That's that's a valid question, but we haven't quite gotten there yet.
And another question, what is this G tilde thing? What is that?
It, by definition, is a subspace inside the functions. It's all the functions whose Hamiltonian vector field is an element of the Lie algebra. Right? And the point is
this thing closed under Poisson bracket?
Yes. Because if you take the Poisson bracket of two things in there, that will have a Hamiltonian vector field, which is the Lie bracket of the two Hamiltonian vector fields, which has to be in the image of the Lie algebra because it's the bracket of the two things that all right, maybe I went by this too fast. This is an important point, so let me just kind of emphasize it. Anytime I have abelian groups and homomorphisms of abelian groups, then I can define the pullback here to be pairs CB such that if I call this F and this G, F of C equals B of G. Okay, and if G is injective,
I mean G of B, right?
Sorry? I'm sorry, yes, G of B. So this is just something I can always do. This is F twiddle, this is G twiddle. So if G is injective, then G twiddle is injective. And I can think of this as actually a subspace inside C. So this is just a general construction I can do whenever I have an abelian group and two things mapping into it. Okay, now here I'm doing this with the abelian group being the Hamiltonian vector fields and the two things mapping in being the Lie algebra of my Lie group and the functions mapping by taking Hamiltonian vector fields. So this is F maps to X of F. This is, X maps to X of M. Probably if I want to be genuinely careful, I need to put minus signs here to make these Lie algebra homomorphisms. All right, and so you know, my G twiddle, I can think of as pairs F, let me use Y such that the Hamiltonian vector field of F is equal to the vector field on M associated to Y, right? But actually, I don't need to remember what Y is. Y is uniquely determined by F because this map is in this vertical map is injective. Sorry, I always forget that if I point to the iPad, you can actually see where I'm pointing. So I can actually just think of this as the functions such that x of F is equal to y of M for some Y. And which of these is a better definition is kind of your choice, right? All right, and this is a Lie algebra. And as I say, it's sort of maybe when you think about it this way, it's a little easier to see why it's a sub-Lie algebra, right? Because both of these maps are Lie algebra homomorphisms. And so naturally the pullback, you can do the pullback in the category of Lie algebras. You get a Lie algebra here. Okay, and there was this horizontal map here, which is just remembering Y, forget what F is. And that's a Lie algebra homomorphism, but it's not injective. It has kernel given by the constant functions. So inside here, right, there's an element given by 1, 0. So take a constant function, or you could have written C over any constant C, and take the 0 element in the Lie algebra. Well, the Hamiltonian vector field of a constant function is trivial. So that's perfectly valid element of this guy, G twiddle. And so the way I kind of like to think about this is that a choice of this mu, this map to G dual, is a splitting of this surjective map of vector spaces. And so this thing I was saying about, oh, you can choose a basis of the Lie algebra and choose what happens arbitrarily on that's a special case of the general theorem that if you have a surjective map of vector spaces, it always has a splitting. And the proof is choose a basis of the image and choose a pre-image of each of the basis vectors. All right, are there any questions? This is like very, very easy homological algebra. Right, this is actually some general statement about maps to projectives, but every vector space is projective, so not an issue. All right, and there are some people out there who I think would tell you that's the definition of a moment map, a vector space slitting of the map from G tilde to G. But there's an additional compatibility that people usually ask for and which Canis de Silva uses as part of the definition of a moment map. So the manifold M has an action of the group G. The dual of the Lie algebra G star has an action of G by the coadjoint action. And so a moment map, well, this condition is something that satisfies this condition 1. This is the condition we already talked about of corresponding to a Hamiltonian function for each element of your Lie algebra, but which is also G equivariant. It's kind of a natural thing to ask for in addition to just encoding Hamiltonian functions for each of the elements of your Lie algebra. You're mapping from something that has a G action to something else that has a G action. You should ask that it's G equivariant. And I'm just writing here in equations what it means that it's G equivariant. So when you apply the map to G times some point, you get G acting on the image, in this case by the coadjoint action. And you can kind of dually write this in terms of the adjoint action, if you want. So this has to do with, if you take your Hamiltonian function and you pre-compose it with the action of G on your manifold, well, you aren't going to get the Hamiltonian function back if G is non-abelian. You won't get a Hamiltonian function for the same element of Lie algebra, but you might get one for a different element of Lie algebra. So that's the definition of a moment map. And a Hamiltonian action by definition is a symplectic action with a choice of moment map, which I'll just remind you goes from the underlying manifold to the dual of the Lie algebra. All right, any questions? So this is sort of saying a Hamiltonian action, it's a choice of Hamiltonian function for every element of your Lie algebra, but it's ones that somehow play nicely with each other, where the whole thing is compatible with the action of the group. Okay, so one important but very simple example, if I have T star R3, so I mentioned that this has symplectic actions of R3 induced by translation on the base and of SO3 induced by rotation of the base around the origin. So if I do translation, then the moment map is pretty simple, right? I think we already talked about this when we talked about integrable systems, that the symmetry of translating the coordinate comes from the conserved quantity of momentum along that coordinate. So on R3, what that means is I think of T star of R3 as R3 cross R3, the first one being the space coordinate X, second one being the momentum coordinate Xi, and the moment map just forgets X and only remembers Xi. So part of where this name moment map came from is that's the linear momentum for the particle moving around. On the other hand, if we think about SO3, okay, then we have to think more carefully about what's going on. And I'm both going to go through this fast, but I kind of wrote out the details a little bit to make clear what's happening. The Lie algebra SO3, so SO3, the Lie group, let me just remind you, I think I said this in words, but let me just say it again. It's matrices in GL3 such that A inverse is equal to A transpose. And additionally, I have to assume that the determinant of A is 1. That's what makes it SO3 instead of O3. When I take the derivative, that becomes the condition that I'm anti-symmetric. And so I picked some coordinates here in anti-symmetric matrices. Yes, there's a reason that it's minus Z3 here and Z1, Z2. It has to do with the kind of conventions around cross product, etc. And you can check that when you use these particular coordinates, the Lie bracket, actually taking commutator of matrices, gets identified with cross product. And so I sprinkled these minus signs in here so you'd get cross product on the nose and not some weird signed version of it. So the Lie algebra of SO3 is actually isomorphic to R3 with Lie bracket given by cross product. And somehow the way to think about this is the vector in R3 is the axis that you get rotation around when you exponentiate. So again, that's why you have to put the minus signs in the right place. So that's really the thing you get. And you get all the handednesses right, that it's right-handed rotation around that vector with your thumb pointing in the direction of the vector. Indeed, that's sort of what happens with cross product. It has something to do with, you take two vectors and you think about what would happen if you rotated a little bit around one and then a little bit around the other and then back around the one and then back around the other. Now, if you go through, and I actually did kind of write this out a bit here, what the moment map for the action of SO3 is, it's again cross product. So I think of T star R3 as, one copy of R3 corresponding to the position, one copy of R3 corresponding to the momentum. And if you kind of do everything naively, you find that the moment map is take the cross product of the position and the momentum. And that has a name in physics, that's angular momentum. All right, and becomes a little bit unpleasant to write out all the details, but here's sort of one example, and all the other examples will be this with indices permuted, right? That here's my formula for the cross product of X and C. So in order to check that this is a moment map, what do? I take the three individual components, I think of those as functions. I find their Hamiltonian vector field. So here I'm taking the first component. I find its derivative, its differential, I should say, and then go to the Hamiltonian vector field. And it turns out that's exactly the generator of rotation, right-handed rotation around the x1 axis. All right, cool. So this explains why we actually use the term moment map, because these two most fundamental examples give us the two kinds of momentums we're used to in classical mechanics, linear momentum and angular momentum. And there's some funniness around the name moment map that some people, I think this is dying out over time, but some people say momentum map. And I had, I took symplectic geometry out of exactly the same book with Alan Weinstein, who's sort of one of the originators of the field. And I think he sort of said it was his fault that he had originally translated, called this a moment map, and then changed his mind that it should be called a momentum map. And for a while, everyone at Berkeley said momentum map, and people on the East Coast said moment map. And the issue that this was originally a French term, application moment. And the difficulty around translating this, I discovered this when I was preparing for this course, that I had thought that this was just kind of a dumb mistake, that people had seen application moment and said, oh, moment map. When, actually kind of in context, it should have been momentum. But it's actually much more confused than that, because in French, there isn't a single word that describes linear and angular momentum. And so momentum map can't be correctly translated back into French. And so if you kind of literally translate application moment, moment map is the right translation for it. And like in French, you wouldn't call linear momentum moment, but you would call angular momentum. But in context, momentum map probably actually does make more sense. That's really kind of the idea it was trying to get at. But at this point, moment map is totally universal. I think it's one, and that's what I'm used to saying because I learned symplectic geometry out of this book. But just something to be aware of. You may see momentum map out there, and it means the same thing because of this funniness about translating from French. All right, I think that's an opportune time to take a break. Yeah, I will. Resume recording. Unfortunately, as any of you who went to watch the recording noticed, last time, Wednesday before last, I forgot to restart the recording after the first half of class. So fortunately, I only recorded the first half. Sad. I knew it was going to happen eventually, but hopefully that will be the only time, but at least I didn't miss the whole class. All right. So one example that's useful is when you have the action on the cotangent bundle, and actually these formulas both for the linear and angular momentum are special cases of this. If you have an action on X, and you look at the induced action on T star of X, that's not only always symplectic, it's always Hamiltonian. And I think probably you can derive this from the fact that the symplectic form itself is always exact. But there's an actual formula for the moment map, which is basically at each point, well, we have a point in the base and we have a covector. And the action on the base gives us a tangent vector to the base for each element of the Lie algebra, and you just pair that with the cotangent vector. So it's kind of the only formula you could come up with that uses all of these ingredients in the right way. And another example is that if you look at sp2n acting on r2n, that always has a moment map where you take your element of the Lie algebra of sp2n, you apply that to the vector, and you take the symplectic pairing of the vector, and there's a 1/2, because 1/2s always show up all over the place. I should mention this is actually, so probably in this conversation I had with Hugh, probably there should have actually been a 1/2 here. Yeah, that seems right. Basically to account for the squared. So in the case where n is equal to 1, sp2n is the same as SO2. It's that circle action. And you're just acting on R2, which you can think of as C. And you can check that this formula in terms of the symplectic form using the compatibility of the complex multiplication and the symplectic structure, this is actually 1/2 norm squared. So in the n equals 1 case, it's 1/2 norm squared. All right, so those are lots of interesting examples of symplectic actions which do have moment maps. Are there any examples where they don't? And the answer is, well, yes, of course. We wouldn't have made such a big deal about it if there weren't a few. So we can look at R2 acting on itself by left translation. So its action is symplectic, and of course on R2, every symplectic vector field is Hamiltonian. Of course, I'm using the obvious volume form on R2 as my symplectic form. All right. On the other hand, if we had a moment map, that would have to give us an equivariant map from R2 to the dual of the Lie algebra with the adjoint action. So my manifold is R2 with R2 acting by left translation. The thing I'm mapping to, the dual of the Lie algebra, well, that's also R2, but it has the trivial action. R2 is a abelian Lie algebra, so its coadjoint action is trivial. So any equivariant map has to be constant, and it's not going to be a very good moment map then. So in this case, there's no moment map. If you sort of think about, another way to kind of think about this is, think about this translation action, think about the Hamiltonian functions you could get. They're linear functions. And so you're looking for linear functions that are invariant under translation. Well, there aren't any of those except the constants. So in this case, we have no moment. So most interesting symplectic actions have moment maps, but very far from all of them. Let's see. So just a useful thing to know. I think I thought I was going to use this somewhere. Maybe I didn't end up doing so, but a useful thing to know. Moment maps are compatible with restriction to subgroups. So if I have a closed subgroup inside a Lie group, I get a sub-Lie algebra. And so dualizing, one of the nice things about the fact that I took the dual, means I get a map from G dual to H dual, from the dual of the Lie algebra to the dual of the subalgebra by restricting linear functionals. And so if I have a Hamiltonian G action, I get a Hamiltonian H action by restricting the action and then composing with this projection to H star. Sort of a useful thing. So for example, like this moment map we found for SO3 also gives us moment maps for each individual circle of rotations in SO3 by projecting to the correct coordinate.
Sorry, I have a question again.
Mhm.
Just kind of stupid question. You said you complained about this case of R2 acting on itself, and you said you just it would have to be a constant, and you said, well, that wouldn't be a very good moment map. Do you mean that isn't a moment map? It doesn't satisfy the criteria?
I mean right. I mean that being a moment map requires satisfying two conditions. And the argument there is if you satisfy condition 2, then you are constant and you don't satisfy condition 1.
Oh, okay, thank you.
Right? So yeah, to maybe say a few
okay,
more words
yeah. Sorry,
here.
so your constant, so your differential is 0, right?
Yeah.
Okay, yeah.
Yeah, you would need that, mu 1, 0 is equal to x plus some constant c, mu 0, 1 is equal to y plus some constant d. Well, those aren't constant. They aren't constant as functions, so they don't give you a moment map.
Right. Okay, thank you. Sorry.
Yeah, no, it's okay. I understand. All right, any other questions? All right, so I think we have enough time to cover when do moment maps exist, and when they exist, how unique are they? So, as I said, I really like to think about moment maps in terms of I have this map from G twiddle to G, so G twiddle being all of the functions whose Hamiltonian vector fields are the image or something on the Lie algebra. And well, we talked about the fact that having a map that satisfied condition 1 was just a vector space splitting of the map from G twiddle to G. Now, getting a moment map that also satisfies condition 2, that's also equivariant, just means, well, you need to have an equivariant splitting of that surjective map of G representations, where the Lie algebra is endowed with the adjoint action, and G twiddle has the action that comes from the fact that it's a bunch of functions on a manifold with a G action. All right, so this is just kind of a rephrasing of that condition 2, right? So a map with condition 1 is a vector space splitting from G to G twiddle. It's for every element of Lie algebra. I, in a linear way, choose a function that it's the Hamiltonian vector field of. And condition 2, equivariance of the map, is true if and only if this splitting, did I give this a name? Mu star. I'm calling this mu star because I can think of this as pullback of the elements of the Lie algebra, thought of as linear functions on the dual of the Lie algebra, to the manifold, to functions on the manifold. This condition 2 is equivalent to mu star is equivariant, i.e., it's a map of representations. So this is really the existence of a moment map is a question about a map of representations of the group G splitting. So, right, there are various kind of ways to moment map exists if and only if the constants inside G dual have a G invariant complementary subspace. Right, and that'll be the image of the map mu star. So it's one of these sort of standard bits of linear algebra. If I have an invariant complementary subspace to the constants, there's a unique mu star that it can be the image of. And if I have a mu star, its image gives me an image.
Sorry, quick question.
Mm-hmm.
Yeah, it's not immediately clear to me how G acts on G tilde. The group acts on these Hamiltonians. I mean, you say that it acts on these functions by just pulling back the function, but could you just convince me that indeed keeps you within G tilde?
Well, right, when you pull back the function, one of the vector fields coming from the Lie algebra, that's the adjoint action on the Lie algebra, right? So the reason it has a G action, right, is I constructed it as this pullback, and everything in this picture has a G action, right? The Lie algebra has the adjoint G representation. The Hamiltonian vector fields have the action by push forward. I maybe have to be a little bit careful that inverse is there or something, but the functions have the pullback action. So all of these maps are already compatible with the G action. And so the pullback has an induced G action.
Okay, thanks.
Whoa, sorry about that. Weird freeze up. All right, so this is sort of something I just want to sit with a moment because it's one of these things that like I don't think Kenneth De Silva explains it very well, and it's kind of something that makes the problem seem much easier, right? That you actually, this is just a question about I have a couple of finite dimensional vector spaces. I have a map from one to the other. I have G actions on both of them. And the question is, like, does the kernel have a G invariant complement or not? In particular, there are a lot of tools of representation theory you can bring to bear on this. And so that covers existence. The other question is uniqueness. Uniqueness is very easy. So if a moment map exists, then there you can get any other moment map for the same action by just taking a G invariant map from the adjoint representation to R, or that would be a G invariant element of G dual, and adding that to your moment map. So that you can easily check that gives you another moment map. And to see why that's all of them, it's useful to just kind of think about splittings of short exact sequences of vector spaces in general. So this is just to kind of, in case you're not used to thinking about this language, a quick reminder, if I have a short exact sequence of vector spaces, so this map of U into V is injective, and this map of V to W is surjective, and the image of the map for U is the kernel of the map to W. A splitting is a map back the other way such that the composition going around this loop is the identity on W. And you can construct such a splitting, one for each complement to U as a vector space. And the set of such choices has a regular action of a set of linear maps from W to U. So this is something I leave you to check. If I have two such maps, the difference between them is a map from W to U. And if I have any such map and I add a homomorphism from W to U with it, I'll get another such map. So this is kind of a standard thing that there's no canonical choice of splitting usually, but if I choose one, then I can get all the other ones by adding homomorphisms from W to U. And none of these facts change when you add in G equivariance, except that you have to look for a G invariant complement and have G equivariant maps from W to U. All right. So in particular, one really nice thing about this is that quite often the Lie groups in question that we'll be interested in have this property of being reductive. We call Lie group reductive if every finite dimensional G representation is semi-simple, which means that any invariant subspace has a complement. I think I didn't finish this sentence. Any invariant subspace of a G representation has an invariant complement. So any compact group, so UN, SUN, ON, SON, SN, SN raised to some power, are always reductive. And the same is true of GLN for R or C, SP2N for R or C, SON for C, which is a well-defined thing, but not compact. On the other hand, if you have the additive group of Rn, that's not reductive. So there are plenty of non-reductive Lie groups out there. And somehow this Rn is actually like the representative example. If your Lie group is not reductive, it's because something like Rn is showing up somewhere in its composition series. All right, so if G is reductive, then the existence of a moment map is automatic, right? The existence of a moment map is something about having a invariant complement to one particular subspace in one particular representation of the group. But if the group is reductive, that must happen. So if G is reductive, then any G action automatically has a moment map as long as the vector fields all land in Hamiltonian vector fields. And, many of the groups we want to consider acting on things are reductive. For many of us, non-reductive groups are not something we're going to think about all that often. Some people like them a lot, so it is relevant, but this is certainly a very powerful theorem that tells you a lot of the time you're going to have a moment map. Another kind of useful way to think about this is that this space G twiddle is itself a Lie algebra, with the Lie algebra structure given by Poisson bracket. And this map from G twiddle to G, that's a Lie algebra map, and its kernel is central. Its kernel is the constant functions. So they have trivial Poisson bracket with everything. They're central, and this is what we call a central extension of Lie algebras. So kind of another perspective you can think about is this is a split central extension of Lie algebras. So if a moment map exists, then it's a trivial central extension. And I should emphasize this Lie algebra structure in G twiddle, that's part of the G action on G twiddle. That can be gotten by taking the derivative of the G action. So it's sort of, it's storing all the information about how the connected component of the identity of G acts. So the kind of the only difference in thinking about this, does the central extension split and does my map of representation split, is if your group G isn't connected, then the other connected components are going to add in some information you'll only see in the first version. So if G connected, then actually there's a moment map if and only if this central extension is trivial. All right, so one more example I wanted to do, yeah, not too bad, is the case of this translation action on R2, right? So we should see an example where this doesn't work out. So in that case, G twiddle, that's the span in the space of functions of 1, X, and Y, right? So we already saw that X and Y give us the two generating vector fields for our function. Adding, so taking a linear combination of them will get us all possible elements of the Lie algebra, and then I can add constants to those any way I want. And when I take the Poisson bracket of X and Y, I get 1. So this is a non-trivial central extension. You can check, and it's what's called the Heisenberg Lie algebra. So I should say it's isomorphic to the Lie algebra of strictly upper triangular 3x3 matrices. With this guy corresponding to X, this guy corresponding to Y, and this guy corresponding to 1. So actually, I think the right way to do this would be to say A, B, C. Hopefully I will get my signs right. Okay. Those two, AX plus BY plus C. There's some chance it should be minus C, but I think I got the signs right. So yeah, this ends up being a non-split central extension, and this guy is a representation of R2 where the constants don't have an invariant subspace. So you can actually check how the adjoint action works here. And the problem is that I can't do something like look at these guys. We're setting C to 0 because that's not an invariant subspace. And you would need to have a complement that looked something like this. But it's not, there's no invariant one. All right. So the last thing I'll note here is essentially you can always fix this issue about the moment map if you're willing to replace the Lie algebra by the Lie algebra of the central extension. So what you always get is a map from M to G twiddle star. You know, in this case being, you know, R2 mapping to R3, but it's going to be mapping in as X, Y, 1. So this is, think of this R3 as the dual of the Lie algebra. And so the dual of the Lie algebra of R2 is like the level where this is 0. But where this moment map gets sent to is the level where it's 1. So, you know, somehow the existence of a moment map is always this thing about, well, like, well, if you add in this central extension, you can always do it. And the question is just, is this central extension 0 or not? Are there any questions? Finished up a little early there, so I'm happy to talk about this a little bit. Maybe it's worth thinking about what I was saying here about the adjoint action. So, you know, if I take this guy and get the adjoint action, I'm going to write this as multiplying by, so I send my element of R2 to this guy. I'm putting the star in the upper right-hand corner because the entry there doesn't matter, and it will just annoy me to put something there. It'll just make the formula for the inverse more complicated. So what I'm doing here is I can identify R2 with the matrices of the form all ones down the diagonal, zeros below, X and Y right above the diagonal. And then I mod out by the normal subgroup given by 0, 0, and star here. So this quotient I can identify with R2. Think of it as a subquotient of this matrix group. And that's useful because, you know, this is getting me something that's sort of compatible with this map from G twiddle. And when I do this action, what do I get? Well, I get, oops, 0, 0, 0, 0, 0. A, B, those don't change. But in the top right-hand corner, I get C plus BX minus AY. So what I'm seeing here is I'm getting a representation of R2 where modulo this line given by the top coordinate, I get the trivial action, which is the adjoint action of R2. But then this top line has this kind of weird property where you act non-trivially on it depending on what these other coordinates are. I mean, I could have all phrased this in terms of a non-split central extension. I mean, I can see the non-splitness right away because my G twiddle is a non-abelian Lie algebra, and my G was an abelian Lie algebra. So something really funky must have happened with the bracket to go from an abelian thing to a non-abelian thing. It's not just a direct sum of the two-dimensional abelian Lie algebra with the one-dimensional abelian Lie algebra. So this is kind of another manifestation of this, right? That so, you know, I have my constants, oops, get identified with this guy. Oops, that was way too many zeros. Get identified with things of this form. And that's a perfectly good invariant subspace. But to have a complement, I would need to have a subspace of the form, here's AB, and this guy here somehow depends linearly on A and B. Lambda A plus mu B. For A and B in R. That's what a complementary subspace to this guy would look like. And well, you can just look at this formula and see there's never going to be something where that's an invariant subspace, because you can get anything you want in that top right-hand corner as soon as either of A or B is non-zero. Right? So if I try to come up with a two-dimensional subspace that does this, I'll immediately be forced to throw in another vector and get a three-dimensional subspace. All right.
Question.
Mm-hmm.
So you said if you don't have a moment map, if you don't have this equivariant splitting, that you can just take the G tilde and you get something like a moment map. So
Yeah.
like, how is that not a moment map? Like, can you, like, what does your original group action become? Can you integrate the action of G tilde and get it and make it an actual moment map now?
That's the thing that makes me slightly uncomfortable. As in, you know, what's the most general statement you can make along those lines? So if your Lie group is connected, then there's no problem, right? Then basically
then you get a moment map for a different group action though, right?
You get a moment map for a different group action, yeah. You know, I think like you could also just define what it means to be a moment map where like the group and the Lie algebra don't quite match up, right? Like you could, if you wanted to, define the notion of a moment map where instead of mapping into the Lie algebra of your group, you map into the Lie algebra of a central extension of your group. That's like a, you know, pretty natural notion. Saying central extension there is useful because if you have a central extension of a Lie algebra, the adjoint action factors through the adjoint action of the, I have to be careful, it factors through a Lie group whose Lie algebra is the guy you were extending, right?
Like what's the relation between a group who's, you know, a group with some Lie algebra and it's some other group whose Lie algebra is a central extension of that Lie algebra? Like, what do you, if you extend the Lie algebras, what does that do to the groups?
Well, right. I mean, sort of.
Are there examples of like, I don't know.
Yeah, I don't have an extremely good answer.
You get what I mean?
I mean, somehow the point is like the thing that naturally comes out of this geometric picture is you have, you know, you start with a Lie group acting on a manifold.
Yeah.
And what you get out is a central extension of its Lie algebra, which has an action of the original group that like is compatible with the adjoint action on the Lie algebra for the original group. And I don't know that there's like a kind of cleaner way to package that information than just saying that, right? Saying that you have a Lie group and saying that you have a central extension of its Lie algebra that the group itself acts on. So this is one of these things where like, I'm not sure what the kind of absolute cleanest way to package the information is, right? But somehow what comes out of the geometry is this extension. All right, any questions?